about the shortcut rules for differentiation, starting with the derivative of a constant. Remember, derivative, d over dx also represents the derivative. So I could write, like, for example, I could either write dy over dx. I haven't used that notation that much so far. Just know that this is nothing different than writing y prime of x. So y prime represents the derivative of the function y. Also, I could write dy dx, which means the derivative of y with respect to the variable x. And you know, that notation is actually especially helpful because it's kind of like delta y over delta x, except that we're taking a limit as that increment delta x is going towards 0. But just know that d over dx also gives you the derivative of something. It's just another notation to do the same thing. Okay, so speaking of the derivative of a constant for our rule number 1. And if you've seen these rules before, would you please refrain from answering, because then I think it's really easy for you guys. Let's try to have everybody else, those who haven't seen calculus before, think a little bit harder on these. What do you think is the derivative of a constant? A constant function would be just like a horizontal line, something like, say, 5, y equals 5. What do you think is the derivative of that line? Or the slope of that line, right? That's what a derivative is, right? For a line, it's easy. For a curve, we have to do more work. But what is it? What is the slope of that line? Anywhere you are. It's 0, right? So basically, let's make a note that derivative of a constant will always be 0. Because that's like finding the slope of a constant line, a horizontal line. Okay? How about rule number 2? Say that you have the derivative of mx plus b, which is a line, right? Mx plus b represents a line where m is the slope of the line, right? So what do you think is the derivative of a line, a slanted line? Any thoughts? I heard a good suggestion already. Any other suggestions? For a straight line, it's really easy to find instantaneous rate of change, right? At any given moment, it's always the same, right? Rise over run is always a constant, no matter where you are on a line. And what is that constant equal to? The slope, m. So the derivative is going to be that slope, which is m. By the way, we could easily use the limit definition to prove each one of these. All you have to do is like take x out, replace by x plus h, etc. Go back to the basic definition, and you will be able to show through analytical methods how these rules are derived. Okay, so if we have just a line mx plus b, the derivative is going to be its slope, because for a straight line, the slope at any given moment is a constant. Okay. What if you have something like x to a power? Now, we've already worked on some of these cases. For example, we've done if y equals x squared, what was the derivative there? dy dx or y prime was 2x. Okay. I'll give you a few more examples. If the function is x cubed, I don't know if maybe there was one question from the homework that used a cubic function. It gets really messy because you've got to extend x plus h to the 3rd power. They get very messy very quickly after the 2nd power. But let me just tell you at the moment so that you can see a pattern. It's going to be 3x squared, the derivative. I'll give you the next one also, so see if you can give me the general pattern. If y equals x to the 4, its derivative is, any guesses? 4x cubed. That is correct. Now, what about the general rule? If you have x to the n, what do you think will be the derivative based on these pattern we see here? Yes, Adam? Precisely, n times x to the power of n minus 1. Basically, if you had to write a rule for this, you would say, when we differentiate a power function, x to a power, you bring that power down and you subtract 1 from the power, and that's how you come up with the derivative, so you don't have to apply the long method. In a minute, I'm going to show you the analytical way to get that answer, okay? But right now, let's just do a few practice problems. For example, let's do the derivative of x to the 7. What is the derivative, d over dx, of x to the 7th power? Applying this rule that we just learned, a very basic rule, it's going to be 7 times x to the 6th. None of that long limit definition, much easier to do. What if we have this one? The derivative of 1 over x. How do we do that one? The derivative, d over dx, of 1 over x. Okay. When you have a situation like this, when x is in the denominator, to make it look like this rule, you needed x on the top, so rewrite it first. So before we differentiate, we're going to first rewrite this expression. So 1 over x is the same thing as x to the minus 1, right? Would everybody agree? Okay, now let's apply the power rule. So you want the n times x to the n minus 1, so there's going to be negative 1 times x to which power? We need to subtract 1, so to the negative second power. And on all of these examples, I will ask you to write your answer without any negative exponents, please. Okay, so if you can rewrite this again, how would you rewrite it? And don't forget the negative up front, so it's going to be negative 1 over x squared, right? Basically, the negative 2 exponent means bring that quantity down as a positive exponent as x squared, but x or negative 1 up front still remains. Now, remember that question from the last group activity we had? I think it was a part D or something, like 1 over x. We did all that work to simplify right here in 2 seconds. The answer is negative 1 over x squared. So it's really a tremendous saving in time. Yes? Yes, because first you bring the power down, which is negative, right? And then you subtract 1 from the power, following directly this rule over here, right? So the power became negative 2. This negative still remains there. But the negative exponent, that's pushing the quantity to come into the denominator, so that's why we ended up with negative 1 over x squared.
Oh, because like 1 over x technically written as
That was the first step, right?
Yeah.
Right. Then we brought the power down and subtract 1 by 1. Right. Okay. Let's do the next one. Let's do the derivative of the square root of x. Once again, before we find the derivative, it helps to rewrite it as x to a power, because we're going to apply the power rule, which is rule number 3. So we're going to, first of all, rewrite it as x to the 1/2, right? That's what root x is. Notice that in that step, I kept my d over dx notation because I haven't yet taken a derivative. I've just rewritten the inner portion, right? In the next step, I'm not going to have d over dx notation because now I'm actually taking the derivative in the next step. Okay, so applying the rule, what should I be writing? 1/2 times x to the power of, we want 1/2 minus 1, right? And what is 1/2 minus 1? Negative 1/2. Now we need to rewrite this without a negative exponent. There's already a 2 in the denominator from that 1/2. And x to the negative 1/2, when that comes in the denominator, how will it come as? 1 over the square root of x, right? Because basically you could first write it like this with a positive exponent, x to the positive 1/2, but then that's nothing but the square root function, so you might as well just put it as 1 over 2 times root x. Remember, this was another one of your messy group activity questions from the last time, maybe part C or something. Again, with this technique, it's very easy. Now, on the test, yes, I will ask you some questions using the long method, but once you know the shortcut rules, at least you can check your answer, and if it doesn't match, you always have a chance to go back and fix your work and try to catch what happened wrong there. If it's square root of x, I would prefer to see it with the radical placed in. That would be better. But usually my general rule of thumb is I just don't want to see any negative exponents. Okay, like if it was like x to the 3/2 or something in the denominator, you could either leave it like that, or you could just, like, let's just do a quick review of exponents. If it was x to the 3/2, how could you write this as a radical expression? The 3 is the power and the 2 is the root, right? So this would be the same as the square root of x cubed, correct? Because 2 is the root and 3 is the power. And then there are many ways you could go about leaving this answer. You could put the 3 on the top of everything. You could take out something from the radical. But right now, I'm not going to get into that. All I'm saying is, if you're a fractional power, you can leave it as a fractional power or as a radical. But for square root of x, it's so simple. I always want you to see the square root of x in the final answer, if that's what we have. Okay? Yes, questions, Sandra? Good question. Just know that if you were trying to, like, the question was, how do you know when to rationalize or not? Usually, if as a final answer, you can leave it like that in my class. I'm not very picky about rationalizing the denominator. That's like a historical reason. It was more difficult to divide by, let's say, root 3 than to multiply by root 3. So before calculators, they did, they went to great lengths to rationalize denominator. But like if you are doing something where you have like 0 over 0, you have no choice. You got to go further. There you could multiply the top and the bottom by the conjugate. But in general, if you just have like root 3 on the bottom, like it's okay. In my class, you can leave it as, like in this case, 1 over 2 root x. That's not a problem. All right. How about the derivative of 1 over x to the third power? The derivative of 1 over x to the third. So once again, let me give you a moment. Rewrite and then apply the power rule, please. So 1 over x to the third. First, we're going to rewrite it. How would you rewrite 1 over x to the third? First, just to rewrite it, it will be x to the negative third power, right? Now differentiate it. So we bring the power down. We subtract 1 from the power. What do we have? X to the negative 4. When you rewrite it without a negative exponent, it's negative 3 divided by x to the positive fourth power. Okay, so this was just a basic power rule. And before we go to the next example, I want to quickly show you where this power rule comes from. Let's see. Just know that every rule that we're learning today, if it's a rule about differentiation, it comes from that basic definition, limit as h goes to 0. So if your function was x to the n, how would you apply that definition of a derivative to that function x to the n? Limit as h goes to 0, right? If you have nothing else, no other way of finding the derivative, you would do the long way, which would be f of x plus h minus f of x over h. If you like this one, just watch this one. Don't try to write it because this is going to be messy. I'm sure it's in your textbook if you need to look at it again. This is just like an FYI. Just know where these formulas are coming from, okay? So we're going to go back to the basic definition. What should I have as my first term now for my f of x plus h? Good. X plus h to the nth power, right? Because this is x to the n we're talking about. And then minus x to the n all over h, right? Okay. Now, how do you distribute x plus h to the nth power? Let's think about that for a minute. Like, let's do a simple example. Like, what if you had x plus h to the third power? How would you simplify that? The first term is what? X to the third, right? What is the next term? You know, some of you will remember Pascal's triangle, you know, to get the coefficients from there. Like, Pascal's triangle was something like this. 1, 1, 1, 1, 2, 1. You keep adding the previous rows. 1, 3, 3, 1. So to do the x plus h to the third, you got to follow this row, right? 1, 3, 3, 1 as the coefficients row. So the next coefficient should be a 3. And you keep subtracting the power of x and increasing the other power. Like, it'll be x squared times what? H to the first, right? Plus the next one will be 3 x times h to which power? Second, and the last one will be 1 times h to the third. Now, everything except for the first term has an h in it, does it not? And look at the second term. Now, the second term is very much revealing. So the second term, you see the 3x squared h? And we know the derivative of x cubed will end up being 3x squared, right? Everything comes from that second term. Why? Because when you expand it out in general in terms of n, the x to the n's are going to cancel. Like if you were doing the third function, you have an x cubed coming from here and then minus x cubed coming from there. They would cancel. You're left with this next term, which is like over there, it was 3x squared h. Now everything else is an h in it, so which means you can factor out an h from everything else that is remaining. So if you were to factor an h, so this is already gone, okay? If you were to factor an h out of this, that would be 3x squared, right? And everything else though will remain, will still have an h in it. All the other terms will have an h in them. So as h goes to 0, the h's you factored out, they disappear. These disappear. However, when you let h go to 0, everything that has an h in it is going to become 0, 0. The only thing that doesn't disappear is that term, n times x to the n minus 1. Up there, that would have been 3 times x squared portion. So that's, again, a little bit theoretical. It's going a little bit deep, but I know some of you are at the level you can understand a proof like this. So at least I want to show you where these rules are coming from. So at the end, then we say that derivative of x to the n is n times x to the n minus 1. It all comes back down from that binomial expansion of x plus h to the n. Okay, we'll go back and do some more examples. Let me clean up this a little bit. Okay, we're going to do some more examples about shortcut rules today, and there's a few more rules I want to give you. Okay, here's your rule number 4. The derivative of a constant multiple, like c times f of x, where c is a constant. The rule says, again, every one of these rules you could prove by that basic definition. But the rule says that you can pull the constant outside. You see, the c can be taken outside and then multiplied with the derivative of the inside function. So it's very different than rule number 1, right? Rule number 1 was when all you have is a constant, then the derivative is 0, right? But if you have a constant times a function, then what you have is you can pull the constant outside basically and differentiate the function. For example, derivative of 3x squared. So pull the 3 outside. And just find the derivative of x squared right now. What is the derivative of x squared? AJ, would you agree that this would be 2x? Right? The derivative of x squared is 2x, right? So basically saying that keep that constant as it is and multiply it by the derivative of the inside, which is 3 times 2x, or that's equal to 6x. So what would you tell me, for example, for the next one? 5x to the 4th. What would be the derivative of this expression? So the constant remains. You differentiate x to the 4 and multiply it by that constant. So do we all get 20x cubed? Okay. And in the future, you may want to do this in one step. Just eliminate this middle step I have here. Just when you bring the 4 down, it's going to get multiplied by the 5. So you write down the 20 and subtract from the 1 from the power. That's your x cubed. Okay. All right. Another simple rule that's going to make our life easy is the derivative of a sum or difference. When you have derivative of f plus or minus g, basically you can distribute the derivative over a sum or difference. Take the derivative of the first plus or minus the derivative of the second. For instance, the example I have below is kind of like a repeat of the examples, the 2 examples from the top. So let's write down the answer. Since we have a plus between the expressions, we can go one piece at a time, basically. Differentiate the first piece plus differentiate the second piece. So what will it be? 20x cubed plus 6x, correct? So if you have a plus or minus, you can go term by term. We'll do more examples of this, such as in this example that we have at the top of the page, let's find the derivative of 7x to the 5 minus 4x squared plus a third x cubed. This one we'll use, as you can see, a little bit of everything we've learned so far. Minus 2 over x squared plus 5 over x. I'm going to give you a little time to think about this, and we'll come back and discuss it. So I will first rewrite and then differentiate. The first three terms, there's nothing to rewrite as far as I'm concerned. But the next one, I'm going to write as negative 2 times x to the negative second power, right? And the last one, 5 times x to the 1/2 power. I kept my d over dx up front because I haven't yet differentiated this. In the next step, I'm going to not going to write it because I'm going to differentiate each term one at a time. So let me know what you guys got for the first term. 35x to the 4th minus 8x plus 3 over 3, which is going to be 1, right? Then x to the 2nd minus 2 times x to the power of, actually, that's negative 2 times negative 2. Let's make that plus 4 times x to the power of negative 3, right? We're subtracting 1 from the power. And the next one, 5/2 times x to the power of negative 1/2. Now I need to rewrite this. By the way, suppose I had one more term at the end. Say I had a 7, the 7 by itself. In the next step, the derivative of that would be 0. I don't even have to mention that in the next step, right? If it's just a constant all by itself, the derivative would be 0. What if I had something like this? Say plus 7x or something at the end there. What would the derivative be then? It would just be 7. This is like mx, right? Derivative of m times x is just a slope, or 7. Or if you're applying the power rule on that, the power is 1, right? If you bring the power of 1 down and subtract 1 from the power, you have like 7 times x to the 0. That's also 7, right? So we didn't have to deal with that in this case, but you may need to deal with that in another problem. Right now, let's just rewrite everything. Okay, with the negative exponent, it's going to go down to the denominator as 4 over x cubed. And the next one as 5 over 2 times the square root of x. Okay, did we all get the same answer here? Okay. Again, as you can see, these are not difficult, but they can get a little bit tricky. Sometimes they give you like x to the 3/2 power or something in the denominator with more fractions. You just need a lot of practice on them, so make sure you do all the homework and group activity problems, because this is kind of like building the foundation of calculus. After we learn these rules, every section we cover, we're going to be taking the derivative as the first step of a problem. So you've got to be really, really strong in applying these rules that we're learning today. Recognize this problem appearing here in red. Negative 16t squared plus 500. This was the example I used as our introductory example last class, Introduction to Derivatives. We did the long way, first numerical, then analytical. We got like negative 96, if I remember correctly. Now we have the shortcut rule. See how quickly we can get the instantaneous velocity with the shortcut rules. So to find the derivative with respect to t, what would be the derivative of the first term? Negative 32t. Derivative of a constant of 500 is 0, right? Now we want to evaluate this at the point. I can sometimes put a line here and on the bottom say evaluated at t equals to 3, because they want to know the velocity at the third instant. Just multiply negative 32 by 3, and voila, we got it. So as you can see, shortcut rules are really great time savers. But again, we owe it to mathematicians. If they didn't see these